Hello everyone, welcome to our first lecture on sets. As I said in the instructions, you're more than welcome to stop the recording when I introduce a new definition to just go over it yourself in more time and really internalize the definitions, as this might be a little faster than the usual lecture pace because I don't have to write it all out. Okay, so we'll start with the first definition, which is the definition of a set. So a set is just a collection of mathematical objects, and the member of a set we call elements, and then we write x element x to mean that x is an element of x. Another notation we should be all aware of is the following. So if I want to have the set containing, for example, the elements A1, A2, A3, rewrite curly brackets open A1, A2, A3, curly brackets closed. And in the same way, we can also look at the set which contains infinitely many elements. So let's say the set containing A1, A2, A3, and going on for each natural number, rewrite curly brackets open A1, A2, A3, and dot, dot, dot. Note that in this way, we cannot just write every set. For example, the real numbers cannot be enumerated like this. Then furthermore, sometimes we want to just write a set of elements that have a certain property. So let's say this is the set of all x's such that x has property P. Sometimes we restrict this, so we're saying that we only take elements out of a already chosen set x such that x has property P. So what do I mean by that? Let's do a quick example. What could we have here? Let's take all natural numbers such that the element is a prime number. Okay, so in this case, your x up here will become the set of natural numbers, and your property P means is prime. Okay, so then let us see some other important sets that you probably already know of. So which are those? Well, we can look at the empty set, just the set that contains no elements at all. We have the natural numbers, the integers, which are the natural numbers together with 0 and all the negative numbers. We have the rationals, which are a quotient between an integer and on the bottom the natural numbers. So see here, we choose the natural numbers, so that includes not dividing by 0. So this is. And then we have the real numbers, which are not easily described in the way above, but we probably all hopefully know what they are. And then we have the set of complex numbers. Okay, great. Again, feel free to pause the video at any time to see what's going on. So now we get to our second definition, the definition of a subset. So if we have two sets given, x and y, then we say that one set is a subset of the other if all elements in x, so if a z is an x, then this is also an element of y. And we write here x subset of y to denote x is a subset of y. And here's some attention that you want to look at. In the literature, there's sometimes different definition of this over here. So sometimes x subset of y means x is not equal to y. So it means strict, let's say proper. proper subset. And then they write X subset and then a little bar underneath Y to mean X subset of Y or X equal to Y. So important for us, X subset of Y is the same as X subset of Y with a bar. So we do not distinguish between them. And so now we learn our first proof strategy. So one reason I first start talking about sets and functions is precisely this. So I want you to learn a little bit on how to write proofs and give you guidelines on how to do this. And this is really one of the main things I want you to learn in this class, yeah? How to write a proof, how to come up with a proof, and a little bit of proof writing etiquette. So let's see what we have here. So our goal is, we want to show that an X is a subset of Y here. Okay, so the first thing is we always want to start with our assumptions. Then the second thing is we kind of want to let the reader know what this actually means. So what do we really have to do? And this is our second bullet point. So we must show that if Z is in Y, then Z is also, if Z is in X, then Z is also in Y. So let's start out by taking an element of Z. And so now we get to the fourth bullet point. And this is the thing that gets tailored to the situation you're in. So here I just wrote insert mathematical arguments to show that now Z is in Y. So this depends on the specific situation you're in. And then you always want to conclude with the statement. Okay, so this is the specific proof strategy for this, but there's something you can see here. So proof writing, you should really think of it a little bit as like writing an essay. It's not just a bunch of mathematical arguments putting one after the other, yeah? You should think of it as having a beginning. So the beginning means you kind of lay out what you want to prove, what is given, and so on. Then you have the main part here, where this is actually where you do mathematical arguing. Okay. And then you have an ending where you summarize what you have shown. And so this is nothing specific to this proof strategy I wanted to introduce here. This is something you should always keep in mind when you write a proof. You want to start with your assumptions. Then in the middle, you want to argue why whatever you want to show is true. And then in the end, you want to summarize what you have shown and let the reader know you're done. Okay. So next thing we're going to do is put this in action. So we want to show that a certain set is contained in another set. So let's go to the proposition 1.3 in our lecture notes. So here we have two sets. Let A be equal to the set of integers, and we demand two properties. So the first property is that Z is actually greater than 0. And z is divisible by 4. And then we have a second set, b. This is going to be all natural numbers such that n is divisible by 2. So now we want to conclude. So I'll let you guess what is contained in the other. Yeah. Okay. I guess you also know A should be contained in B. So now we want to prove this. And you might want to pull up the proof strategies because I don't have that on this page anymore. If you can, on the side. And I really want to go along the bullet points. So for the moment, I'm still going to write the proof in this manner. You'll see that in the next lecture, we'll drop the bullet points and just write it as one big text. So what was the first bullet point? So we say we wish to show that A is contained in B. So it's up to replacing x by A and y by B. It's really the same thing. Okay, then the second bullet point, we repeat this. So we're really just copying the guidelines. So by definition, we must show that if z is in A, then z is in B. So now let's go to the third bullet point. And this again is just copying. So suppose that z is in A. Now we get to the fourth one and see here, and for this I'm actually going to go back. We are here now, and this is where we have to tailor it to our specific situation. So now I'm going to insert some arguments. Okay, so we see what's going to happen. So we want to use that z is in A. So as z is in A, and we're going to unravel the definition of A. So the definition of A ensures that what? Z is an integer and greater than 0. And z is divisible by 4. And now we're going to translate this. So this first part here, z is an integer greater or equal to 0. This just means z is a natural number. And then we go to the second one, z is divisible by 4. Well, how can we write this? This will tell us that there's some integer such that z is actually equal to 4 times that integer. So, and the latter yields an integer n in z such that z is equal to 4 times n. And now this 4 times n, I can also write this as 2 times 2n. Well, and now we have everything for b in here. What do we have? We have that z is a natural number, and z is, well, 2 times something, which means z is divisible by by 2. And now we get to the last bullet point, our conclusion. So now we conclude that Z is in B. And so we have shown that A is a subset of B. And at the end of a proof, I make a little box. This middle box is the same as, you could also write Q, E, D. Okay, I will stick with the box. And the box will just indicate that your proof is done. So now we have shown it. And so now you might want to take the time and go back and compare these two. And you'll see that the first 3 bullet points and the last one is just really copy paste. And then every time I'm making these insert mathematical arguments is where kind of you have to come up with your own wording and arguments. Great. And so next, let me just put out this list here, which kind of gives you things that are important during a proof and things you probably have seen in the previous proof. So what do? We always state what we wish to demonstrate before doing so. We unpack and use the definitions where necessary, which just happens a lot of time. And we try to highlight when we're doing so, unless sometimes we think maybe the reader can figure it out itself without any help. But you should always assume that you write your proofs to another student in the class. So you really want to put in as much detail as possible. You should always state what are your assumptions. You sometimes prove if and then statements. So things like if Z is an integer greater than 0, well then Z is a natural number. We use modus ponens. You'll see this later on, that this is something like if you have a basis, then this tuple is also linearly independent. You deduce things from assumptions that you put up beforehand. You lose mathematical equations, and then again, and I want to stress this again, is you always want to summarize what you have done. So as an exercise at home, I would recommend you to just go back to the previous proof and find a sentence that corresponds to each of the bullet points up here. And so next, let's go to being a subset. So we want to look at the next definition. Being equal, 2 sets being equal. So suppose you have 2 sets X and Y. We say that X is equal to Y if each of them are subsets of each other. And then we'll write, as you probably would assume, X equal to Y to mean that X is equal to Y. And so here we're going to get our second proof strategy. And we want to write down how we want to prove that 2 sets are equal to each other. And this looks fairly similar to what we've done before, but there's also something new coming in here. So the first 2 bullet points are pretty much the same. We let the reader know what we want to show. So we wish to show X is equal to Y. Then the second bullet point is just writing down what this means from the definition. So by definition, we need to show these 2 things, that X is a subset of Y and Y is a subset of X. And then, well, here we use that we already learned how to do certain things. So this refers to our proof strategy 1 now. So we want to show that X is a subset of Y. So we insert a proof that this is true, and then we insert a proof for y being a subset of x. And then as before, once we've done this, we want to write a conclusion. We have shown that this is true and so on. So again, yeah, I can't stress this enough. A proof has a beginning and it has a conclusion. So now let me give you some examples of sets that are equal. So first of all, let me just give you two different ways of writing down the same set. The first one is going to be all natural numbers, and we add two properties to it. The first one is going to be n is actually less than 17. And the second is that n is prime. And now I'm going to write the set differently, and I'm just going to put all the prime numbers that are less than 17 here. So this is going to be 2, 3, 5, 7, 11, 13. Okay. Then secondly, and I think this is a little more interesting, let us start out with the following set. So let's say 8, 1, 2, 1, 2, 8, 4. Okay. Now, you can see that I put 8 here twice. And what else? I put 2 here twice. And 1 here appears twice. But there's something important about sets is that they cannot see if an element is in it twice or 3 times or something like this. Yeah. Either an element is in or not. Yeah. If you go back to the definition over here about being a subset, it's very far there, over here, then well, it really just takes an element in X and shows that it's in Y. But well, if one is already in X, then one is in Y. If it's one more time in X, it will still be in Y. Okay, so long story short, we can just enumerate every element once. So let's say we have here 1, we have 2, we have 4, and we have 8, and that's it. So before we see a proof of two sets being equal, let me give you one more definition. It's the last definition of our lecture of today. And so here, what do we have? We're gonna define what it means to be a union. So the union of two sets is just a collection of elements such that it's in one or the other. The intersection here is all elements that are in both. And this one here, which might be a little bit less familiar with, is the so-called takeaway. And what elements are here? Well, you take all elements which are in the first set X here. So this refers to Z and X. And then you take away all elements that are in the second set. So this is coded by Z, not an element of Y. So here, I define this below here. If you put a bar through the element, that means X is not an element of Y. Again, pause if you probably need a little bit more time to internalize these. Okay, and then we'll get to the last part of the lecture, which is the De Morgan rules. And this here will be done in the TA lecture on Thursday. And homework. So one of them is going to be covered in the TA lecture and one of them is homework. You can also find the proof though in the lecture notes. Okay, that is all what I wanted to tell you about sets, and then I'll hopefully see you Wednesday to answer all the questions you have.